Hello, and welcome to this video lesson, which is concerned with showing you the King-Altman method for deriving the rate equation when we have uncompetitive inhibition. Now, to start with, we're going to think about our enzyme, which we're going to symbolize as we've been doing with a capital E, colliding with substrate according to rate constant K1 to form the ES enzyme substrate complex, which can dissociate back to free enzyme and free substrate according to rate constant K2, or go on to form product according to rate constant K3. So we regenerate free enzyme and we form product. Now in the case of uncompetitive inhibition, the enzyme substrate complex can combine with an inhibitor according to rate constant K5 and form the ESI complex, which can dissociate according to rate constant K6. Now you might be wondering why we have K1, K2, K3, and then we skip to K5 and then K6. And the reason why is because even though we're showing the conversion of ES to enzyme and product as a unidirectional process, and hence the double-headed arrow, we're reserving the chance or potential for if a full treatment where we would have the dissociation according to K4. And so this keeps the odd numbered rate constants moving forward, if you will. So that's why we skipped to K5. So let me erase this just to show you that we're still considering a steady state situation, and we start the reaction without any product. We only add substrate to the free enzyme, and we either form product, or perhaps when we form this enzyme substrate complex and we add some inhibitor, then we can form an enzyme substrate inhibitor complex, ESI, and that would be illustrative of uncompetitive inhibition. Continuing on, I've redrawn our kinetic mechanism, and now we're going to rewrite it in a manner that focuses just on the different forms of the enzyme, which is our typical first step when we use the King-Altman method. So we have E, and we have ES, and we have ESI as our three different enzyme forms. And so E can be converted to ES via K1 times the concentration of S. Remember, that can dissociate, the enzyme substrate complex can dissociate back to free enzyme and substrate via rate constant K2, or it can go on to regenerate free enzyme plus form product according to rate constant K3. But now with an uncompetitive inhibitor according to rate constant K5 times the concentration of inhibitor, we can form the enzyme substrate inhibitor complex, which can dissociate back to the enzyme substrate complex according to rate constant K6. So this is our geometric pattern, and it's not easy to describe. I guess we could call it an oval with a tail. So we're going to use this pattern nonetheless to inspire us to come up with some King-Altman patterns that importantly will not contain closed loops. So we could imagine a pattern like this, or we could imagine a pattern like this. So in either case, we we follow the upper oval and then we have the tail, or we follow the lower portion of the oval and we still have the tail. So we have our two King-Altman shapes shown here. Continuing, I've redrawn our pattern that concentrates on the different enzyme forms, and I've also redrawn the two King-Altman patterns, which, as we keep stressing, do not contain closed loops. So now the next thing we want to do is write our distribution equations, and our first one is concentration of E as a fraction of total enzyme concentration, E sub T. Oops, let me clean that up. Okay, and that is equal to, remember we typically just call the denominator for now delta, and it's something we're going to construct, and as we've shown before, it's going to end up being the sum of all the numerator terms of our distribution equations. And this time we're going to have three distribution equations because we have three different forms of the enzyme, E, ES, and ESI. So for the E over ET distribution equation, we want to think about the different ways we can end up at free enzyme. So using the upper pattern, we could go K6, whoops, let me erase that, I don't want to confuse it, but I'll just retrace it actually. We're going to go up K6 and then over K2. So K2 times K6, because we multiply K2, or excuse K6 times K2, and I do it in increasing numerical order just for convenience. And because they're part of the same pattern, we multiply them. And again, let me try to clean up my writing here a little bit. The other pattern, the lower pattern, if we follow it, we would have K6 and then K3. So we're going to add this other route, and we're going to call it K3 times K6, again, increasing numerical order, but we followed this pattern up according to K6, and then we followed the lower oval according to K3, and we multiply those two rate constants together because they're part of the same pattern. So that is our E over ET distribution equation. I am going to erase and kind of clean up our patterns, and then we're going to write our other distribution equations. So let me do that. Now our next distribution equation is going to be, E S I over ET and that's going to be something over delta. And so now we want to think about the different ways to get to ESI. And we can use the top pattern. We can go K1S times K5I. So K1, K5, S, or IS. It doesn't matter because we're multiplying everything together, but I like to keep the rate constants in increasing numerical order. So this was K1S, K5I, and that got us to the enzyme substrate complex using the upper pattern. Now, we cannot use the bottom pattern because remember, that is a unidirectional arrow. K3 is a unidirectional arrow, and if we're starting at enzyme and we're proposing to go to ESI, we would have to be going in opposition to a unidirectional arrow, and recall that from our previous discussions that we are not allowed to do that, and therefore this bottom pattern is not available to us in this distribution equation. So once again, I'm going to erase real quickly, clean this up, and then we'll write our last distribution equation. Okay, our last distribution equation is ES over ET, and it's going to be something over delta, and remember delta is just going to simply be the sum of all the numerator terms, and we want to think about how can we get to ES, and can we use both patterns. So we could use the top pattern because that would be K1S and then K6. So it's going to be K1 times K6 times S, and that again I like to keep the rate constants together, but everything's multiplying each other because they're part of the same pattern. So again, I'll reiterate, K1S along the upper oval, and then coming from the bottom of the fit pattern, K6. So that gets us to ES, and that would be K1, K6 times S. Now once again, we cannot use the bottom pattern because to do so, we would be going against a unidirectional arrow. So we only have the one term in the numerator for the ES over ET distribution equation, and that is K1, K6S over delta. And so delta is going to be the sum of the numerator terms, and we'll continue on a new screen. Continuing on, I have written out our rate equation, and so we have lowercase v for velocity and dp dt for the product rate of appearance of product, and that is equal to K3 lowercase rate constant lowercase 3 K3 the rate constant times the enzyme substrate complex. And then the problem is we don't know what the concentration of the enzyme substrate complex is, so we're going to substitute in an alternative expression for that. So I've done that on the right here. So I have K3, and then the rest of this expression is an alternative expression based on our distribution equation for ES as a fraction of total enzyme. I brought over fraction of total enzyme on the right, and then everything else would be the numerator term, K1, K6S, over delta, and delta is the sum of all those numerator terms from the previous screen. Now what we want to do now is simplify this equation, and we can't get S completely by itself, but what we can do is get the term that only contains S in the denominator by itself. And in order to do that, we're going to multiply the numerator and the denominator by 1 over K6. When we do that, we get significant simplification, basically. So what I'm doing is showing you the result of multiplying the numerator and the denominator by 1 over K1 times K6. So let's rewrite this. It's a little messy. We're going to say the velocity is equal to K3, and I'm going to write ET next to it because we're multiplying everything in the numerator. The order is not important, but the order will help us make connections to what we've seen previously. So K3 times ET times S over K2 plus K3 over K1 plus, I'm going to factor out an S. So I need a parenthesis, and I'm going to have 1 plus, and I'm going to write inhibitor concentration, and I'm going to write that over K6, and then I'm going to write underneath that K5, and I'll explain why I'm doing that, but I want you to see that algebraically it's okay, because if we look at the upper equation, K1 appears in the numerator multiplying the inhibitor concentration, and so it's okay to bring it down below the denominator term. Algebraically, that's equivalent. Let me close the parentheses, and then I'm going to factor out my S, which is what I said I was going to do. So this still looks a bit clunky, but I want you to see that we have some simplification. I'm hoping that you recognize K3 times Z total as V max, and I'm hoping that you recognize K2 plus K3 over K1 as our Michaelis constant, capital K subscript M. And then this might not be as obvious, but if you go back to our original kinetic mechanism, you will see that K6 over K5 is a dissociation constant, and it's a special dissociation constant, and we're going to call it capital K subscript I for the dissociation of the inhibitor. And I'm going to add a prime because if we were doing the case of competitive inhibition, we would also have a capital K subscript I term. And to distinguish the two, I'm going to use capital K subscript I for competitive inhibition and capital K subscript I prime for uncompetitive inhibition. So on the next screen, we'll rewrite this, and then hopefully this will look familiar to you. Okay, so here we go. Lowercase italicized v for velocity is equal to V max, V max times the substrate concentration, let me clean that up, over the Michaelis constant Km, K subscript M, plus, parenthesis, 1 plus the inhibitor concentration over Ki prime, close parenthesis, times S. So there it is. There is the derivation of the rate equation for the case of uncompetitive inhibition using the King-Altman method. Now, we're not going to show a justification of this method. Instead, we're going to refer you to a paper that appeared in the Journal of Chemical, let me clean that up, Journal of Chemical Education, which is abbreviated as JChemEduc, and that was the year 2009, and the volume was 86, and the pages are 385 to 389. Now, if you consult this paper, you will see a justification of the King-Altman method as applied to the case of competitive inhibition. But using that and thinking of the steps to derive the case for uncompetitive inhibition, which we've shown on this video, you can apply the justification shown in this paper and see that we are on firm theoretical basis using this method as well.